Bem-vindos a todos ao segundo simpósio brasileiro de cálculo fracionário. Welcome to all on the Brazilian Symposium Fractional Calculus. In this moment, we are the presentation of Professor Dr. Nasir. All participants are asking Professor Nasir before your presentation.
Good morning, everybody. And maybe good afternoon and good evening also. It is good to have you all to meet you in the Brazilian Symposium on Fractional Calculus. We are now in the Middle East country of Oman, where the time now is 4 o'clock in the afternoon. Now, coming to the topic, my topic is the new fractional linear multi-step method with improved stability, in which we are going to construct a fractional linear multi-step method of a new type, new category, and a new method of order 2, which has some better stability and computational properties. My topic of presentation will be fractional initial value problems, fractional linear multi-step method, and especially the Grünwald-Letnikov approximation and superconvergence, which is what we are interested in, and using this to construct our new method. And we are also categorize the fractional linear multi-step method already known in the literature through subclasses. And from this subclassing, we will see that our method is a new subclass. And we will give some numerical verifications and stability regions and comparisons also will be given. Now, fractional derivative definitions, we know that the Riemann-Liouville fractional derivative and the Caputo fractional derivative are given through the integral formulations. And the Grünwald-Letnikov definition is given through a difference formula like this. This is a shifted Grünwald-Letnikov approximation where shift is R, and the G, K, beta are the coefficients given by this, which can also be obtained from a generating function 1 minus z to the power of beta. Now, this superconvergence property of Grünwald approximation is our interest. So the Grünwald approximation of fractional derivative will be given by this simply by dropping the limit of the definition of Grünwald-Letnikov. And when the R shift is an integer, this gives an order 1 approximation. However, when the shift is non-integer, like beta by 2, at this special point, the Grünwald approximation gives an order 2, which usually is called superconvergence. And we are going to use this idea of superconvergence to construct our new method. So let me introduce the fractional initial value problem, which is of this form, which can be converted into a homogeneous initial condition form also. So we will be considering this form equivalently with this form. And fractional linear multi-step method have two ways of approximation. One is to, one is to write the fractional initial value problem into a Volterra integral equation and approximating them. Lubitsch have done a lot of work on that. And another way is to directly approximate the derivative in the initial value problem by an approximation of the Grünwald type. So this is what we are interested in, and if we can consider that a fractional linear multi-step method will have a general scheme like this, where W, K, and sigma k are coefficients of some generating functions. The most general form of the generating function will be like this, and this can be written in this form according to Lubitsch also in their formulation, where A, B, P, Q are polynomials. So it's a rational polynomial to the power of alpha with times another rational polynomial. So the existing fractional linear multi-step method can be categorized based on this general formulation. So we have divided the FLMM into some subclasses. The first one is the fractional backward difference method. We already know that this has a form that polynomial to the power of beta, and this polynomial A will be the backward difference method for classical initial value problem. That's the generator of that problem. Fractional Adams and fractional Adams-Moulton and fractional Adams-Bashforth methods come under another subclass, where the generating function will be having this form. A denominator part has a polynomial here. There is another subclass with the rational polynomials like that, which was obtained by Aceto by approximating the FBDF subclass generating function by some Pade polynomial, rational polynomial approximations. When you do that, the order of the method reduces. It doesn't give the same order as in the FBDF class. So if you want to get much closer to that order, then you have to have higher degree polynomial. So some difficulties are there. And the last category that we see is the fractional trapezoidal rule, which comes under this category, where A and B are polynomial to the power of beta, and the fractional trapezoidal method is the only one of this category as far as we know. Now, based on this idea, our new method will not be among these subclasses, and it's going to be a new one. Now, to motivate our idea, we first consider the superconvergence and then approximated in some way, where we got the fractional Adams method and fractional Bashforth method. So this was the motivation of obtaining our new method. So let us explain this first here. This is the superconvergence approximation of the Grünwald-Letnikov, where you can see that the right-hand side has a non-integer shift part. So this Fn minus beta by 2 is not aligned with the computational domain nodal values. So we approximate this using Taylor series approximations into an order 2 as a linear combination of two near values. Fn and Fn minus 1 can be used to approximate Fn plus something. And if you choose u, mu, and n differently, you can have two different approximations. One uses Fn and Fn minus 1, and the second one uses Fn minus 1 and Fn minus 2. So if you substitute these two into this equation, we get two methods. One of them is the implicit fractional Adams-Moulton method of order 2, and the other one is a fractional Adams-Bashforth method of order 2. These were already established by some other means, but it can be obtained by superconvergence also. That is our point here. Now, our new scheme uses superconvergence in another form, where the right-hand side Fn is in the computational nodal point, but y will be shifted. So this is an adjustment by some shifting to get the y part has the shifting here. Okay, earlier we had the shifting here, and here is the integer part of that, but now we have the other way. So since this is now not aligned with the nodal points, we will approximate this using this approximation. And if you substitute it back, we will get this formula. So here we have this linear combination coming in y, not in f. And if you drop this and then use the approximation notations at all, and finally we get our new method like this. So here is the method where the right-hand side has no linear combination. The y value has the combinations here. That's it. And we computed some examples, and we are presenting one of them here, a nonlinear fractional initial value problem of this type, where f ty is this, which the exact solution can be given by that. So we are solving the nonlinear equation arising from the FLMM by the Newton-Raphson root finder method. We are not going to use the correct method. Anyway, we have computed the solution for nearly many subintervals computational domains for the various alphas 4, 6, 8, and 1. And you can see that all of them have the order 2 in this case. So it is truly a second order method. But now, well, other methods are also second order, so there is nothing important here. But when you consider the stability analysis, we have something. So first, let me explain the stability definitions and so on. The test problem is this, and its solution is this, where E beta is the mid-Leffler function. And the analytical stability region for this function is this, sigma beta is equal to this. And the numerical stability of an FLLM can be defined by that, where pi is the generating function of the fractional linear multistep method, as we have explained before. Now also we define another region based on an arbitrary alpha. For an angle alpha, we define this region. So now the definition of stability comes under these categories. An FLLM is said to be A alpha stable if this S alpha is a subset of the numerical stability region, or A is stable if the analytical region is a subset of the numerical region, and unconditionally stable if the negative real line is in the stability region of the fractional linear multistep method. So based on that, we have compared our method with the FAM1, it's a fractional Adams-Moulton method, and these light-colored regions are the unstable regions. So we can see that the unstable region of our method is much smaller than the unstable region of the fractional Adams-Moulton method, which means that the stable region is larger in our method. And interestingly, we have also computed the stability region for alpha equal to between 1 and 2 also, although it is not in our interest now. We see that for between 1 and 2, our method still has an unbounded stable region. very big stable region. The unstable region is bounded. While the fractional Adams-Moulton method has the stability region is bounded, so it is not unconditionally stable. It is conditionally stable, as we already mentioned in this case also. Okay, we have compared with other existing methods also with our method, and one of them is a trapezoid rule of order 2. Fractional Adams-Moulton method already we have compared with that, and we also took FBDF2 also, fractional backward difference method of order 2. And as beta tends to 1, we see an interesting observation that our method will converge to the backward difference method, while FAM will converge to the trapezoidal method. And we can see that in the next slide of comparison. So here the unstable regions are shaded here. The green one is for the backward difference method, and the blue one is ours, and the red one is the fractional Adams-Moulton method. So when beta goes to 1, this is 2, 5, 5, 7, 5, and 9, 5, and so on. So you can see that the fractional Adams-Moulton method unstable region gets larger and larger, and it covers the entire right plane. But on the other hand, our method and the FBDF get closer and closer to each other and finally coincides. So our method is very much close to the backward difference method, but backward difference methods coefficients are computationally a little expensive. So ours is simply a linear combination of the simple Grünwald approximations. That's all what we want to say. Our conclusion is this. We have created a small animation to show how they are going. I will show you after the conclusion here. The conclusion is that a new FLMM of order 2 is proposed from the superconvergence approximation. A new FLMM is of a new subclass. That is a very important part, because the the generating function of this one is of this type, 1 minus beta times a simple polynomial, which is not appearing before in any of the methods. And after that, the new FLM has improved stability properties, as we have shown, and it's also computationally competitive. Now let me show you an animation that you have created. Okay, this is the animation that we have created, and you can see it here. The same thing, but well, as beta moves to 1, the FAM grows, while the FBDF and our new method are getting closer and closer. Although they are just a little bit growing, they finally come to a halt to a bounded region, while the other one, unstable region, is unbounded. But anyway, all of them are A stable. That means it covers the entire left half plane, when A pi by 2 stable. Other than that, ours is very much close to the fractional backward difference method. Thank you very much for your patience. If you have any questions, you may ask.
Dear Professor, thank you for your great presentation, and sorry for our technical problems. I'm impressed by the beauty of the stability graphics. And we have some questions from the audience. May I show them for you?
Right, no problem.
Thank you. I'll show the first one. Question from Felix Silva. In which applications can this method be considered most appropriated?
Mostly, yes. Thank you very much for the question. Then this will behaves like the fractional backward difference method. So any type of stiff fractional initial value problems can also be used by this method, because backward difference methods are very much useful for stiff differential equations, and this is very much close to it. So this can be applied to that. And for application point of view, any initial value problems like what do you call it, fractional diffusion problems, or anything in the anomalous diffusion part, and also control theory problems with the fractional controls, and in many other fields it can be applied. It is a normal, the method, the differential equation is the same. The numerical technique is the one that we are doing newly. Thank you.
Very nice. And we have another question from José Vanteler. What kind of stability are we addressing?
Oh, well, this is the absolute stability that is common for these initial value problems. The zero stability is already there, and we did not talk about that. Not the asymptotic stability. It's also there, but the main objective is the absolute stability. That means that when you make your the number of divisions of the domain becomes larger and larger, that means the step size become very much close to zero. The error goes to zero or bounded. That is the absolute stability. Yeah.
Thank you very much. And there are some comments from the audience. Professor Edmundo is thanking you for the presentation.
Yeah, you're welcome.
And I would like to thank you for the presentation. Indeed, it was very interesting and beautiful. Hope to see you soon, maybe in person here in Brazil.
Yeah, I met Professor Oliveira in France, if I remember correctly, France or Spain, in a conference 2 years back before the corona things. Thank you very much.
Thank you. And I would like to invite everyone to see the next presentation that we will start soon. Thank you once and again, Professor. Thanks.
Yeah.
Have a good conference, everyone.
Thank you.
See you.
Yeah, bye-bye.